In this podcast, we're going to talk about weak acid and strong base titrations. So you start with a solution of weak acid and then you titrate it with a strong base. The equivalence point is going to be above 7 because you know weak acid, strong base is going to make us a basic solution. So above 7 is going to be basic, okay? So basic salt. All right. The big differences between this curve and the strong acid, strong base titration curve is going to be number one, the equivalence point is above pH of 7, and the other is a buffer region exists. Now remember, a buffer region is where you have the solution resist a change in pH. You can still calculate the volume of base that you need to reach the equivalence point using M1V1 equal M2V2. That's because weak acids require the same amount of base for neutralization as strong acids, because as the H pluses come off, they are neutralized, and so you get more and more of them coming off. So it takes the same volume to do that. All right, here is another look at a weak acid, strong base titration curve. And again, recognize that the salt that's produced is what gives us that basic end. When you're doing calculations to determine the shape of a weak acid, strong base titration curve, there are 5 situations in which you might need to get the pH. Initially, you're going to need the weak acid concentration, and to get that, you know that you have to do an ice box with the Ka. At equivalence point, this is when all of your weak acid has been neutralized and turned into the conjugate base. So basically, you can make this into a hydrolysis or a salt problem, and you can attempt to just calculate the pH of that salt. Okay, so the pH of that salt that's produced is going to give you the pH at equivalence point. Halfway to the equivalence point is when the pH is equal to the pKa, or the negative log of the Ka. So this is very useful, especially if you're trying to determine the Ka of an unknown weak acid. Before and after the halfway point, you can use the Henderson Hasselbach equation or an icebox, whichever you would prefer. And then after the equivalence point, you have to know how much strong base you have. So it's the same as what we had to do before with the strong acid, strong base titration curve. So you're going to have to get the excess moles of OH, the total volume of the solution at that point, your molarity of your OH, then calculate POH, then pH. Okay? So you need to know all of that. Henderson Hasselbach equation is an equation that's very useful. It relates the pH to the pKa. And basically, you're taking the base and acid, but you're having to look at the conjugate base and conjugate acid situation. So base and its conjugate acid, acid and its conjugate base. So you're basically looking for an acid and its salt. So here's a good example. So HNO2 and then NO2 1 minus, or NaNO2, whichever you would prefer. Another example would be NH3 and NH4Cl, but now you're dealing with a base, so you would have to change the Ka to Kb, and you'd be working with the the base forms up here, okay? All right, so an example of Henderson Hasselbach, calculate the pH of the following: a 0.75 molar lactic acid solution and a 0.25 molar sodium lactate solution, given that our Ka is 1.4 times 10 to the negative 14th. All right, so we're going to plug all this in, knowing that pKa is the negative log of the Ka, and then we have the log of the conjugate base, and then the acid. Once you plug all that into a calculator, you'll see that the pH is 3.38. All right, another example for Henderson Hasselbach would be the NH3 and NH4Cl. We're already KB, so we don't have to worry about converting to find Kb, but now we have to find Ka, so we can plug it into our Henderson Hasselbach equation. So we do Kw divided by the Kb, and we get our Ka of 5.6 times 10 to the negative 10. And now we're looking at the ratio of the base over the acid. So now we have 0.25 over 0.4, and then the pKa is the negative log of the Ka. Plug all that in, and we see our pH is 9.05. All right, now let's look at an example of a weak acid, strong base titration. So we're going to attempt to determine the pH at multiple points along the curve.